Okay, so we are still in our preparations. We're kind of laying the ground in order to start talking about functions, which we still haven't done. And if you remember from Calc 1, there were some notions and things needed to be defined that played a very important role. For example, what is an open interval? What is a closed interval? What is an epsilon neighborhood of a point? What is a point? And all these things have to somehow be generalized to R2 and to R3, to two-dimensional and three-dimensional spaces. So for example, if you think for a minute, what is the analog of an open interval in three-dimensional space? It's not completely clear how to generalize it, right? Something has to be said, right? You can't just say it includes the endpoints or doesn't include the endpoints. The endpoints of what? Okay, in an interval in R, that's kind of easy to say. So all these things that we're going to define and discuss very briefly fall under the category of what's called topology. Topology is a vast topic in mathematics, and we're only doing a tiny bit of topology only in R2 and R3, only what we need. So after that introduction, let's first define what do I mean when I say R2. I don't think we really wrote that formally. So R2 is the set of pairs x, y that satisfy that x and y are both in R. Okay, so this is R2 as a set. And the space R2, which is the plane, has additional structure on it. So the structure comes from it being what's called a vector space, which is an algebraic notion that you will discuss in more detail in your algebra course. So being a vector space, we can add 2 points, and we can subtract 2 points, and we can multiply a point by a scalar. And if that sounds weird to you, the reason is that we identify the point xy with the vector that starts at 0 and ends at that point. Okay? So that's how this thing becomes a vector space, and that's how we can perform all these operations on it. Okay? Is that clear? Okay, so we think of the point xy in R2 as the vector originating in the origin and ending at the point R2. We identify those two, think of them equivalently, and everything works. Okay? Is that clear? Okay. And in addition to that algebraic structure, where we can add 2 points by adding the vectors, etc., there's also additional structure, which is more geometric in nature. So for example, we can measure the distance between 2 points. Okay? And I'm going to give you some formulas, which you've seen. You're not going to be surprised, but before that, I want to write what R3 is. So R3 is the set of triples, x, y, z, such that x, y, and z are all real numbers. Okay, so these are R2 and R3. And of course, if I would write here R4 or R5, or in general Rn, that would be defined exactly the same way. Okay, and everything that we say here, in fact, can be generalized to spaces, to n-dimensional spaces, and everything works exactly the same. Okay, so we're going to do it just for simplicity. In this course, we're going to discuss mainly these two spaces, and almost everything we say is going to be in this context, but it really can be generalized and very easily. Okay, you just go over your notes, add another letter, and you have R4, and everything works. All the definitions, everything. Okay, so how do we, for example, measure the distance between 2 points? Okay, so we're going to define. Let's move to another board. So how do we define the distance between 2 points? And I'm going to denote them now by x and y. And note that this might be confusing at first, but x is now a point either in two-dimensional space or in three-dimensional space. Let's say three-dimensional. So x is a point. It has 3 components, x1, x2, x3. Or you can think of it as x, y, z, but that would be even more confusing since I'm calling the other point y. So think of the components as x1, x2, x3. and y is a point in three-dimensional space, so its components are y1, y2, y3. What is the distance between these 2 points? And we've seen that already. It would just be the square of the difference between the components. So xy minus y1 squared plus x2 minus y2 squared plus x3 minus y3 squared, and the root of this entire thing. So this is the distance between 2 points in R3, where the first point, so maybe let's write that. X is now x1, x2, x3, and y is now y1, y2, y3. And I might say vector, and I might say point, and I mean the exact same thing. Okay, is this clear? And do you see that this collapses to two-dimensional space if I just remove this term, and then it's the distance between 2 points in R2, and you can easily see how to find the distance between 2 points in R4. You just add x4 minus y4. Clear, everybody? Okay, so once this additional geometry is thrown into the picture, this is called, do you know what for example, R3 with this geometry on it, what it's called? What is its name as a space? It's called Euclidean space. Okay, so R3, for example, R3 with the geometry given by this distance formula that we just wrote is called three-dimensional Euclidean space. And you can replace 3 with any number here, and it would be the exact same thing. This distance formula has a more fancy name. It's called a metric. Any distance formula is a metric. It has to satisfy certain conditions, and those are general notions that can be discussed in topology in general. Okay, so now we're ready to start defining what do we mean by an open set and an epsilon neighborhood and so on. So maybe I'll replace this marker because it's kind of dying. Okay, so our first definition, stop me if there are any questions or if something is not clear. So our first definition is going to be that of what's called an open ball. Okay, an open ball. And it's defined as follows. So let R be some positive number. This is just a good old regular R. It's not the real numbers. And let X be some point, let's say x1, x2, x3, be some point in R3. Okay? And once again, this can be for, I'm not going to say that every time I write something with 3 or 2 components, but I'm going to say it a few times. Okay? So it can be in R2 or in R4 or whatever. We define the ball, denoted by B, centered at, let's denote this by an x naught. Okay, I'm going to add a little 0 up here for the point and for the components. So we're going to denote it by x naught. So this is a specific point. So the ball centered at x naught with radius r, that's what I'm defining, is merely the set of all the points in R3 that satisfy that the distance between x and x naught equals precisely exactly. Okay? So think for a minute about what I wrote here. There's a lot of notation going on here, and in fact there's not a single word in English, oh, except for the word let, okay? And tell me if you can read through all this notation and if what you see in front of your eyes is a ball centered at x0, okay? The set of all points x in R3 whose distance from the given point, oh, I moved the 0 down here, it should be up here, whose distance from the given point, x naught, is precisely r. So what is all the points whose distance from a given point is precisely r? That's a ball. Do you see that? Okay. So this is called, bx0r is called, but that's not what I wanted to say. Oops. I didn't want to say equals r, I wanted to say less than r. Okay? All the points, what I want is all the points inside the ball. Okay? I want the actual solid and everything inside it. So all the points whose distance is less than r. So this is called an open ball. And we'll justify why we call it open in a minute. In a couple of minutes, an open ball with radius r centered at this point x0. Is it clear? Questions? Is everybody with me? Say something. Good? Okay. And if I wanted what's called a closed ball, so this is an open ball. A closed ball, so keep in mind those intervals from Calc 1. When did we call an interval open? When it didn't include the endpoints, right? When did we call an interval closed? When it did include the endpoints. So this ball here, does it include what's going to be defined shortly as its boundary? Does it include the endpoints of the ball? The answer is no, because I'm looking only at points whose distance from the center is less than r, strictly less than r. So how would I define what I would want to call a closed ball, one that does include the points, the endpoints, the boundary? Right, less than or equal to here. Clear? So the ball, or let's say, I don't want to repeat the entire definition, so I'm going to write it in short. If we require the distance between x and x naught to be less than or equal to r, then it is a closed ball. Clear? Do you see the analogy to open and closed intervals? Okay? Okay, good. And specifically, more specifically, so this would be another definition. An open ball with radius. Now I'm going to replace this r, the letter r just came from radius, but now I'm going to replace it with a very special letter which you're all very fond of, with radius epsilon. So we usually think of epsilon as just a small something, right? So an open ball with radius epsilon centered at some given point x naught is called an epsilon neighborhood. This stands for neighborhood. So some words are too long to actually write all their letters. Okay? So it's called, and then you can write it in the English way and in the American way, and there might be some U's there, and so just write the important letters. We can try writing everything just with the important letters. That might be interesting. Okay, it's called an epsilon neighborhood of x naught. So that's the definition of an epsilon neighborhood. Now think for a minute what it was in R, in Calc 1. You took a point, an epsilon neighborhood, where all the points, either to the right up to a distance of epsilon from that point, or to the left up to a distance of epsilon from that point. So it were all the points whose distance from that given point was at most epsilon. That's exactly this. Does everybody see that? Do you agree that this is a reasonable way to generalize epsilon neighborhoods from R to R3, for example? Good? Okay. Now, in fact, remember I said you can write instead of R3, you can write R2 or R4. Let's move one board back here. You can write instead of R3, you can just write R. You can just take one coordinate. So over here you would write X in R rather than, look at this board please. Then you would write X in R such that the distance from X to X0 is less than R. What would that be? What's the distance between 2 points in R? It's just their difference, right? The distance from 5 to 8 is 8 minus 5, right? Do you agree? So that's precisely the root. Let's look even one more board back. Suppose these are just in R over here. What's the distance between X and Y when now they only have one coordinate? It's the root of X minus Y squared. That's a different way of saying absolute value of X minus Y. Do you agree? Okay? So everything works, in fact, even for R, and it gives you precisely the notions which we are trying to generalize. Okay? So everything we write, you should, first thing, before you believe or are convinced that it's a good notion, you should verify that it collapses to the good old notions you already know from Calc 1. Okay? Okay. So now we know what an epsilon neighborhood is. And let's continue with some more definitions. So, yeah, they're different definitions. So, but in fact, I'm going to fill up quite a few boards with definition, 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 and we could have just numbered them. Anyway, x naught, a point, is called an interior point. An interior point of a set A. The set A is now some subset of R2 or R3. Maybe let's write R3. So when I say a set is just a bunch of points. Okay? Not necessarily a ball or a box or an interval or anything. Just a sporadic bunch of points. A point is called an interior point of the set if there exists, do you know how to write there exists in short? Do you know that there's a symbol for that? It's kind of an E but facing the wrong direction. You know this symbol? Everybody? Okay, if there exists an open ball centered at x naught, you can always take open balls centered at x naught, but x naught is called an interior point if there is some open ball centered at x naught which is contained in A. Okay, so let's say we have some set A. Usually my drawings are going to look rather two-dimensional rather than three-dimensional because that's just easy to draw. So here's our set A, all these points. This point is an inner point of this set. Why? Because I can find some epsilon for which the ball, the open ball centered at this point, with radius epsilon is contained in the set A. Is it clear? And this is what makes this an interior point. Good? Now, obviously a point out here is not an interior point, right? But there's also a third kind of points. Those are the points here. For example, the point here. So this point is not an interior point either. Okay, although it is a point of A, but if I take any open ball containing it, any epsilon neighborhood neighborhood of it, even if I take it to be very small, it's automatically going to contain points outside of A. It's not going to be contained in A. Do you see that? So this is an interior point, but this is not. So this dude here is an interior point. And this is not. Clear, everybody? Now we want to give a name to these kinds of points, and these we're going to call boundary points. And the definition of a boundary point is simply going to be points for which every neighborhood, every epsilon neighborhood, contains points of the set and points not of the set, or of the complement of the set. Okay, that's going to be a boundary point. Clear? Let me write that. So maybe we'll erase here. So definition, a point x0 is called a boundary point of a set A if every epsilon neighborhood of x0 includes points from A and points from, how do I say not from A? From the complement of A. Do you know this notation? A with a little c up there. Okay, so this is the complement of A, if you haven't seen it. The complement i.e. Points not in A. Clear? Now let me ask you a question. So we defined what a boundary point is. Is a boundary point itself contained in A? So do you agree that from the definition it doesn't follow? Okay, so a boundary point can be a point in A and can be a point not in A. Okay, so if we take a set A, suppose this is our set A here, and this is a boundary point, I don't know, here's a boundary point. The reason I'm very careful when I draw these sets A, that if I'm not careful, they start reminding me of all kinds of funny things, and then I just can't I just have to, you know, kind of do this and what. Yeah. Okay, sorry. Okay. So that's the set A, and here's a point, which is just a point. Don't think of eyes or anything. Okay, so this point is a boundary point, because every neighborhood you take, and you can say, hey, but that's kind of a big neighborhood. Let's take a very small neighborhood. Maybe a small neighborhood would be contained in A, but no. Even if you take a tiny, tiny neighborhood, it would still have points outside and points inside. Do you see that? Okay, so every neighborhood contains points from A and from the complement of A. Okay, and therefore this is a boundary point, but there's no statement about this point being a point in A. So symbolically, usually we denote, when we draw a solid line, we kind of, imply that the boundary points are contained in A, and if we want to say that the boundary is not contained in A, sometimes we would draw a broken line like this to indicate that these points are boundary points, but they're not in A themselves. But of course, you can have all these points contained in A, except maybe this one, and this one, and there's no good way of drawing that. Okay, so in specific examples, which we're going to see in a minute, we're just going to have to specify what do we want regarding the boundary points. So remark, a boundary points or boundary points are not necessarily, wow, double C, double S, double R. Help me out here. Did I do it correctly? Wow. If that's right on the first try, then I'm very proud of myself. Are not necessarily in A. Clear? Good, everybody? Okay. So, now we're ready, finally, to define open sets and closed sets in general. So definition. A set is called, a set A in R3 is called, any set, any collection of points is called an open set if every point in A, is an interior point. Think Calc 1. Think of the open sets we discussed in Calc 1. Those were open intervals, right? What did an open interval satisfy? That it didn't include the endpoints. It didn't include the boundary of the interval. Every point of the open interval, for every point of the open interval, you could easily find a neighborhood which is contained in the interval. Does everybody see that? Okay, so in R, so this is a remark, in R, we denoted open intervals like this, right? And every point of the open interval, even one that's very close to the endpoint, you can find an epsilon neighborhood contained in the interval. Do you agree? Does everybody see this, or did I make it too small? Good? So an open interval, which is an example of an open set in R, every point is an interior point. Remember that an interior point is a point for which there's an epsilon neighborhood contained in the set. Clear? Okay. This stuff is really easy. Really, really easy when you're going to look at it in a couple of days from now. Okay? Because all I'm doing here is defining things, and these are very, very straightforward, easy to grasp concepts. Okay? The only thing is that we're introducing a lot of new words, and getting used to a new language can take time. Okay, so when I say interior point, for me, I already think I know what an interior point is, but if you haven't encountered interior points until now, then you have to say, what was an interior point? Right, there was a neighborhood of, what's a neighborhood? Oh, right, a ball of radius. Oh, what's a ball? And so that's the only difficulty. If you look at this again in a couple of days, it's going to be just language. Okay. Okay, so now we know what an open set is, and it's a generalization of an open interval in R. Okay. What's a closed set? So a set A contained in R3, for example, is called a closed set. What was a closed interval? it had to contain the endpoints. What is our generalization of endpoints in this context? The boundary. So a closed set is going to be a set which contains all its boundary points. Okay? So a set is called a closed set if it includes all its boundary points. Okay, so in R, that was a closed interval. In R, it was just a closed interval, because its boundary points are only the two endpoints. And in closed intervals, they're contained in the interval. Clear? Raise your hand if you're with me. You're so quiet today. Okay, good. So was that just everybody raising their hands? That's unbelievable. Okay, good, good. I'm happy. Okay, so just some notation for all this stuff. This was terminology. Now we need some notation. So let's throw in the notation, and then we'll do examples. Then we'll do some concrete examples of sets and discuss if they're closed or open or what is the boundary, etc. So notation. So let A be a set. A with a little circle up here is how we denote the interior points of A. All the interior points of A, and sometimes it's just called the interior of A. Okay? Clear? So it's called the interior. This funny letter, which we're in fact going to use a lot in this course, but have you seen it before? So this is not, doesn't have a significant role in Calc 1, but we're going to use it a lot in Calc 2 because it also is used for derivatives of functions of several variables. So it's called del. So this funny letter, which kind of looks like an ear, did everybody get how to draw it? It's fun. Do some of those. So this is the notation for the boundary points. The boundary points of A, and it's just called the boundary of A. Okay, all the points which are boundary points. Okay. A with a bar on top, is called, well, let me tell you first what it is. It's A union, do you know this symbol? Union, good. So it's all the points in A plus union all the points in the boundary of A. So you take a set, it doesn't necessarily include its boundary. For example, it can be an open set. So open sets don't include boundary points because a boundary point doesn't have an epsilon neighborhood, right, included in the set. So if you take A, throw in all the boundary points, include the boundary, then we denote it by A bar, and this is called the closure of A. It's always closed, because a closed set is a set that includes all the boundary points, and here we forced it to include all the boundary points because we just included them. Good? So this is always closed, and it's called the closure of A. Okay? Now just a few remarks. If A is an open set, so this is an exercise. See if you can follow me. It's just a matter of words, a matter of terminology. If A is an open set, then all its points are interior points by definition, right? Every point contains an epsilon neighborhood. So if A is an open set, then its interior coincides with the set. Do you agree? So for an open set, A equals A naught. Do you agree? If A is closed, then it already contains all its boundary points. So if A is closed, A equals A bar. Do you agree? Okay, and there could be any sets in between. Okay, so now with this notation at hand, let's do examples. So here are some examples. So our first example is going to be a sphere. Sphere in, whoop, forgot the H. Sphere in R3. So remember, a sphere is just a ball with some center and some fixed radius. Let's say it's centered at the origin. It doesn't really matter. So let's say it's centered at the origin. So this is the origin, and it has some radius r. And so how would we denote it? It's a ball centered at the origin. So the origin is the point 0, but it corresponds to the 0 vector. Do you agree? And it has some given radius. Let's call the radius little r. So this is little r, the radius. Okay. And it could be an open sphere or a closed sphere. Okay. So how did we... Yeah, that's not... I didn't want that. So remember how we defined the sphere? The sphere is actually the boundary of the ball, right? That's how we defined it. So, so let's be more precise. So B0R, this thing is an open. This was our notation for an open ball with radius, with radius r, centered at the origin, right? And the sphere, so what would be the sphere? Let's call the sphere A. That's the set we're discussing in this example. So this is A. So how would the sphere relate to this ball? A, the sphere, is the boundary of B. B is the ball. Do you agree? Everybody? Now, do you agree that since this is an open ball, this notation we used for an open ball, therefore it's all the points in R3 whose distance from 0 is strictly less than R. So B doesn't contain the boundary. The boundary points, the sphere, are not contained in the set B, in the ball. Do you agree? So do you agree that the interior, so let's add some stuff here. Do you agree first that A, the sphere, is the boundary of the ball? Does everybody agree to this? Okay. Do you agree that the interior of B is B itself? Do you agree to that? Do you agree that the closure of B, the closure of B, which is B union with its boundary, is B union A, because A was its boundary. Everybody good? Okay, can you read through all these symbols and everybody? Okay. And maybe we can add, let's do this. A which is the boundary of B, is the set of all points x such that the distance between x and 0 equals precisely r. That's the boundary. The interior, which is B itself, is the set of all points x such that the distance between x and 0 is less than r. Do you agree? And the closure is the set of all points x such that the distance between x and 0 is less than or equal to r. It's the boundary and the set itself. Does everybody agree to all of this? Good? Okay, let's do something slightly more interesting. You're very quiet today, so I don't really know if I'm just completely boring you out here, or if this is, I don't know, if you're losing me at some point, just say something, make jokes, I don't know. Yeah, question, yes?
Like, is it possible that in calculus 1, for the complement of A, you do not use A bar?
Did you denoted the complement with A bar? Well, I don't know how you denoted stuff. Notation is something that is often very, very, very wide-ranging, and you would find very, very different notations used by different people and in different countries and in various texts. And so I'm trying to use notation, to introduce notation which is as standard as possible, but so whatever I write as the notation I'm gonna use throughout. And in various places where I'm gonna use more than one notation, I'm going to say it and okay. Here's another example. So example 2. Let's take the set A to be all the points x, y. So now we're in R2. Now we're in the plane. All the points x, y. So here's an example of notation. When you write a set, so I'm going to take all the points x, y satisfying that y equals x squared. When you write a set, so this is the set of all the points x, y in R2 such that y equals x squared. You know that, right? You would see texts where this is written like this. You would see texts where this is written like this. I don't know if you've seen that. All different notation for the same thing. Okay? And probably there are many others. I'm going to use this vertical bar to indicate such that. Okay? So what is this? Can you draw this? What would be the picture? So first of all, do you agree that it's in R2? So I'm going to draw it on a plane. And what are these points? What is the set A? Right, it's a parabola. It's a graph of the function y equals x squared. So this is A. Do you agree? Okay. Now let me ask you this. What is the interior of A? The interior of A is the set of the interior points of A. Can you give me a point which is an interior point of A? 0. This point. Is it an interior point? So in order to say that this point is an interior point, right, you're already saying no, but I'm going to explain why you said no, you're right, it's not. In order for this to be an interior point, there has to be a neighborhood of that point contained in A. Is there a neighborhood of this point contained in A? Is there a neighborhood of any point contained in A? Every neighborhood of any point in R2 would include points from A, from the blue graph, and points from outside of A, from the white everything else. Do you agree? So the interior of A is in fact empty. This is the notation for the empty set. This is standard, the only notation I know for the empty set. Does everybody know that? Okay, so the interior is empty. What is the boundary of A? What is the boundary of A? A itself. Every point, here's a point, it's a boundary point, because every neighborhood of this point contains points of A and points from outside of A. Do you agree? Okay, so every point is a boundary point. Therefore, the boundary of the set is the set itself. And note that this is already slightly different than our original intuition of an open interval and a closed interval, right? It's not, this point is not an end point of A in any meaningful definition. Do you agree? But it's a boundary point. Okay, so what is the closure of A? What is the closure of A? So the closure is A when you throw in all the boundary points that they were in to start with, right? So the closure of A is again A itself. Okay? So what can you say about this set A? If it includes all its boundary points already, A is closed. Does everybody agree? Did everybody follow? Okay, so again, it's just terminology that you have to get used to. Here's another one last example for this, this clip, which turned out to be a bit long, but I still need to throw in a couple more definitions. So one last example. So let's look again at a planar set. So I'm going to look at the set. So A is going to be the set of all the x, y's in R2 that satisfy that x squared plus y squared is greater than 1 and less than or equal to 4. So can you tell me how to draw this? It's not exactly a circle. So a circle is x squared plus y squared equals r, right? Or r squared. So what are we looking at here? Right, it's a ring. So if this is 1 and this is 4, and this is a 2 and 3 in the middle, so we want all the points that are whose components x and y satisfy x squared plus y squared is greater than 1, then they're going to be outside of this circle, but inside this circle. So this is 4 here. This is 1 here. And what we're looking at is this thing. And note that I drew the outer circle in bold, whereas the inner circle is dotted, because the points on the outer circle are included, because it's less than or equal to 4. And the points on the inner circle are not included, because it's strictly greater than 1. Do you agree? Okay. So tell me now, what are, let's not write everything, because I think you're kind of getting the concept. What is the interior of this set A? A is all the shaded area. What is the interior of A? Right, the interior of A is everything in this ring except for this outer boundary, right? The interior does not include boundary points. So the interior is everything except this outer circle. Do you agree? Yes? Oh, you're right. Oh my God, very stupid. You're so right, thanks. So this should be 2 and this should be 1. Right? Do you agree? Does everybody agree that this is a better drawing? Okay. So what is the interior? The interior are all the points. Here's a point that has a neighborhood included in the set. So this is an interior point, and this one is, not including the boundary points. Do you agree? Okay. What is the boundary? What is the boundary of this set? On both, right? The inner circle is a boundary, and the outer circle is part of the boundary. Because any point, whether on the inner circle here, or on the outer circle here, every neighborhood of such a point is going to include points from A and points not from A. Do you agree? Good? Can you see this googly-eyed frog here? I just... See that? Well, it has 3 eyes, maybe. I don't know. Okay, anyway. So we know what the interior is. We know what the boundary is. Is this set closed? No, why not? Right, because of the inner circle. The inner circle is a bunch of boundary points which are not included in the set A. So the set A is not closed. Do you agree? Good? Is it open? No. It's not open. Why not? Because the outer circle is a bunch of boundary points that is included in the set A. Right? So there are points that are not interior points in A, therefore it's not an open set. Good, everybody? Okay. Okay, let's just summarize maybe. A is not open and not closed. Okay. So just 2 more definitions that we're going to need. When do we say that a set is bounded? So definition, a set A in R3, for example, is bounded if it is contained in any ball. Okay? So let's look at the examples we already had. This was our first example. Look here a second. This was a sphere. Is it a bounded set? Yes, it's contained in some ball, maybe slightly bigger radius. Do you agree? So this is a bounded set in R3. Let's look at our second example, this parabola here. Is it a bounded set? No. Well, the parabola, what I drew is just part of it. It, of course, continues infinitely in both directions, and it's not contained in any ball. Do you agree? Okay. So although it's very, very slim, okay, it doesn't have any interior points, it's still not a bounded set. So the notion of being bounded and the notion of being big can be different in depending on how you define it, how you think of it. Okay? And what about this ring here in this example? It's bounded. Okay, good. And the last notion that we have, the last definition, a set is called compact if it is bounded and closed. Okay? So the notion of compact is very important in general topology, and it has more general definitions. In Rn, or R2, R3, it simply boils down to sets being closed and bounded, and compact sets are going to have nice properties once we get to discussing functions. Okay, so Clear? Okay, so I know this was rather long. I should have broken it into 2 separate clips, but never mind. So let's stop this here. What I want to do next is discuss sequences. Sequences played a rather significant role, kind of an auxiliary role, but an important one in Calc 1, right? So now we want to spend some time on sequences in R2 and R3.